Hi, my name is Dr. Tammy Campbell, and today I would like to talk about chirality. So what is chirality? Well, it's basically has something that possesses handedness. This something has non-superimposable forms that are mirror images of each other. And so for example, I would like to bring up this two lines. And these two lines reflected in this plane in the center are mirror images of each other, and they're pretty much identical. Even if we were to take the line on the right and flip it 180 degrees and kind of lay it on the line on the left, you'll be able to see that they're superimposable, and so basically these are non-chiral species or non-chiral forms. Now, if we were to take these lines and project them into the second dimension and form these triangles, we would have the same effect. These are both mirror images and they're pretty much identical. If we were to flip one on top of the other, they're superimposable, and so these forms are basically achiral, or they don't have any chirality. An example of this is the amino acid glycine. Now, the amino acid glycine is a prebiotic building block. It's something that's in our bodies. It's one of the amino acids in our bodies. And so it is a building block of life, basically. And so if we were to draw the mirror structure of glycine over here, and so this is the center carbon. I'll bring the H right here. Amine right there. Carboxylate group comes out over here on this side. And then in the back is the other hydrogen. And so these two are mirror images, and if I were to take this one on the right and flip it to look like the one on the left, what you would see is that the two structures are going to be superimposable, and you're basically going to get the same structure because glycine has a plane of symmetry right down the center of it. And so glycine is an example of an achiral molecule. Now, if I were to take one of the hydrogens, say this one on the right, and say if I were to convert it over to, say, a methyl group, you would have a carbon that has 4 different groups around it. This carbon is basically asymmetric, and you will start to see that this carbon has chirality. Now, it's not necessarily the definition that a carbon is chiral if it has 4 different groups around it. There's other forms of chirality, such as what we see in our DNA, in which there's a chirality around a certain center or a certain axes. And that's something that we can discuss later. And so going back to these forms right here, these triangles, if I were to bring them down and say project them into the third dimension and consider the amino acid alanine, a way to look at these forms is to take my hands right here and put my thumbs maybe at the vertices right here. And if I were to wrap my hands around them, you would see that they have mirror images, or my hands have mirror images. However, if I were to take my right hand and put it on top of my left, or vice versa, they are basically non-superimposable forms. And so we are starting to think about forms as being mirror images but non-superimposable, just like what we see in our hands. And so alanine as an amino acid and another building block of life is a great example for this. And so what I want to do for alanine is for the center carbon that we see right there is to draw it in the center of this geometric form, or this tetrahedral. Actually, I will bring it over to this center right there. And here at the bottom, at each of the vertices, I will draw the remaining groups. Hydrogen right here, the carboxylate group right here, the amine over here, and the methyl group in back. And so probably going back into the plane, I can draw dashes coming out over here on this side, and then this is probably within the plane. And so this is a tetrahedral structure and representative of one of the images of alanine. Now its mirror image I will draw on this side. And so we reflect by putting the amine group over here on this side, carboxylate mirroring each other over here, and the methyl group over here, and the hydrogen down below at this vertex. So I'll draw the lines like I did similarly to the structure on the left. And so there you have, once again, mirror images that are non-superimposable. Now, the way that we're able to denote these, I would say, the arrangement of the atoms around this center carbon is through the R or S configuration. And so if we want to know how to assign this as R and S, what we will do is follow the Kahn-Ingold principle, where the highest atomic number usually gets assigned the highest priority. And so the nitrogens both here, and I will draw this in another color, will get assigned 1 and will get assigned 1 here. Now luckily for us, we put the hydrogens at the bottom, and they have the lowest atomic number. And so for the hydrogens, what I would like to do is assign it the number 4, since it's easy, and then we can kind of just forget about it. They're in back of us or they're down below, and we're looking at the triangles above on top. Now, the carbons here are both having the same atomic number, and so we branch out into the next atoms. Here we have oxygen, and here we have hydrogen. Oxygen is higher than hydrogen, and so the carboxylates get the second priority. So we'll put 2 over here, and we'll put 3 for the methyl groups. Now, if we want to assign things that are going clockwise, so 1, 2, 3, so this is basically going clockwise, we give it the signature of R. R meaning rectus, which is Latin for right. On the other side, we have things going in a counterclockwise direction. So 1, 2, 3 is going counterclockwise. And so we assign it the designation of S, meaning sinister, which is the opposite of right. And so R and S basically denotes the configuration of the atoms around the central carbon. Now, another way we can use to describe amino acids is through the designation of L or D. L and D assignments generally come from carbohydrates in terms of glyceraldehyde and the stereochemical configuration of the asymmetric carbon in glyceraldehyde. And that will be discussed in carbohydrate type chemistry. And so from now on, we'll either use R or S or L or D to denote the stereochemical configuration of the alanine amino acids. And so if we wanted to look at alanine, which I would like to say is chiral and also an enantiomer, if we wanted to evaluate the amino acid alanine using physical property experiments such as melting point, or measurements such as melting points or boiling points or thermodynamic measurements, we wouldn't be able to distinguish between these two. Everything would be the same. So if we were to look at something in a chiral or a racemic environment such as this, and say we wanted to use something different like plain polarized light, we still couldn't differentiate between the two. However, if we were to crystallize the enantiomers or the racemic mixture into a pure enantiomeric form, where say we have L in one form, or one experiment, or one beaker you can call it, and say in another beaker we were to crystallize all of the D forms over here. So at this stage, we're going to be able to determine which is which. And one of the ways we were able to do that is by shining plain polarized light onto the sample. And so plain polarized light, once shined into an enantiomeric pure sample, can be rotated either in a clockwise or counterclockwise. So if the L enantiomer is rotating the plain polarized light, for example, in a clockwise direction, then the D enantiomer will be rotating that same polarized light into the opposite direction, or the counterclockwise direction. And so this is very useful, or plain polarized light is very useful for determining enantiomers. Another way to determine an enantiomer is to expose them to I would say, a chiral environment. For example, our bodies are a chiral environment because we are chiral beings. And so if we were to take something like a homochiral polymer, such as proteins in our body, and we were to evaluate what these homochiral polymers were consisted of, we would all seem to realize that they all have the L amino acids. And so the proteins in our body basically only have L amino acids. And so this is very interesting because as prebiotic chemists, we often want to know how did homochirality emerge from basically what could have been a prebiotic racemic world. And I will draw that up here, prebiotic racemic world. And so we have to think about the ways in which this can occur. Because if you think about it, in living organisms, most of the amino acids in living organisms have optical activity and are mostly in the L configuration. In fact, in an organism, once it deceases, the D to L ratio goes from a value of 0 all the way to a value of 1 once the organism is no longer living. And so we want to think about how something can go from an equilibrium process where you have a racemic mixture and go to a far equilibrium process where you have enantiomer enrichment so that one type of enantiomer exists. And so the ways that we can rationalize that this could have occurred is through a process called symmetry breaking. And so in symmetry breaking, one of the things that you would need is biasness. So you would need an environment that biases one of the enantiomers over the other. Another thing that you would need is sustaining that biasness. So you need a method of sustaining it. And finally, what you would need is propagation. So how can we propagate this enantiomer enrichment of one amino acid? And so if we were to have a system, such as the one below, and say in this system we have a racemic mixture of D and L. So I'll write D, and there's no order here, I'm just writing it in a random fashion. And then I'll put L in the other boxes. And so one of the theories in which enantiomer enrichment could have occurred is through space, in which we have a racemic mixture of amino acids and meteorites, and there's circularly polarized light in the interstellar space. And if this circularly polarized light was basically going to hit this sample right down here, and perhaps once hitting the sample, it eliminated a few of the amino acids of the D enantiomer, then what we would get is something over here on the right side where we still have some of the racemic mixture over here. But then we have a little bit more of the L configuration over here. And so we kind of have an enantiomer enrichment mechanism for how homochirality could have evolved, or a homochiral pool could have evolved. Now, another way for this to have occurred is through something similar to this racemization process, except you put this process through heating and cooling cycles or through wet and dry cycles. And over time, maybe there's this little bit of a symmetry break because of these cycles, so that one enantiomer is favored over the other. And this type of favoritism, basically what we call bias, if it's sustained and propagated, will eventually lead to a homochiral pool that would take us all the way over here where we have the emergence of homochiral polymers. And once we get there, we're able to possibly look into ways in which this homochiral polymer could have organized into what we consider today modern life. And so for that, I would like to thank you for your time.